Right, so we continue with colouring. And at the start of this course, I announced, sort of in a sweeping statement, that most of what graph theorists do is relate invariants, graph invariants to each other. And we did touch upon the chromatic number, and have now, in this chapter, related it to the maximum degree of all things. I mean, and even the min degree of subgraphs, the colouring number, a newly invented invariant inspired by the greedy algorithm. And so the theorems we've proved are all of the type saying that if the chromatic number is large, then these invariants are also large. So if a graph has a large chromatic number, it has large min degree, because if it didn't, it would have a small chromatic number. It has large min degree even inside a suitable subgraph. And of course, when you look inside that subgraph of large min degree, you find a highly connected subgraph of that. So large chromatic number implies that various other invariants are also large. It's a strong assumption that the chromatic number of the graph is large. Now, what about the other way? We would like to understand what makes a graph highly chromatic. So this is getting dangerously close to asking why. You don't have children at the right age yet, but if and when that happens, they'll be asking, why is this, why is that? And if I ask you, why is the chromatic number of a graph large, then I'll step out of myself and tell myself off for asking that question, because it's not a mathematical question. Right? There's no logical corresponding notion of the colloquial why in our logic as we have it. Simple example, why is the street wet? Because it's raining? Oh, no, because they forgot to put a roof over it. Right? So why, the answers to why questions depend on context, they depend on what you assume and so on, which is why we don't consider it. All we do consider is implications. So we have necessary implications for large chromatic number. If it's large, then various other things are large too, and we would ideally like sufficient conditions as well for large chromatic number, because a sufficient condition, if it's easily checkable, gives us certificates for the chromatic number being large. Right? So if, for example, if it were true that every graph of chromatic number at least k had a k subgraph, then somebody could persuade us that the chromatic number of a particular graph is large by just pointing to that complete subgraph and say, well, it must be large because here's a complete subgraph of order k. So that alone needs k colors, and therefore the entire graph needs k colors. So such sufficient conditions, if they're easily checkable, would provide certificates for large chromatic number. Of course, we have certificates for small chromatic number, namely easily checkable certificates for small chromatic number. Colorings. If I want to persuade you that a graph needs only 7 colors, I'll color it. Well, I'll show you, please check. There's a coloring, and you can count to 7, I assume. And you can also check adjacency, and you can check that adjacent vertices have different colors, and there you are. Right, so ideally we would like a condition that is both necessary and sufficient. And those that we've looked at so far, large max degree, or in a suitable subgraph, large min degree, or even large high connectivity, is not going to do that for us. There's a simple example, an example of where all these things are large, but the chromatic number is really, really small. Can you think of one? Can you invent a graph of chromatic number 2 that has max degree, min degree, connectivity, edge connectivity, coloring number, everything really, really big? Yeah, K and N, yeah. Okay, so that's not so easy. And presumably such certificates don't exist, but that's another story. Let me give ourselves a slightly different task, and that is to come up with the following pseudo-certificate, and that is a Kuratowski set. So if pk is the class of all graphs whose chromatic number is at most k, then this is closed down under subgraphs. Right? If you can color a graph with at most k colors, take a subgraph, you can still color that with the same colorings. So we might hope to characterize high chromaticity by identifying this. Now that's a big X, that's a chi. The minimal, by identifying the minimal graphs that need more than k colors. Well, that does characterize high chromaticity, right? If a graph needs more than k colors, it contains a minimal graph that does, and that's in this list by definition. And the converse is trivial too. So why isn't that a good characterization? Well, it all depends on this list. Can we write it down? Are there just 2 such minimal things, or 1, as in Kuratowski's theorem? Or maybe there are a few more, but there's an explicit rule of how to construct them and how to check that they're present in a given graph and all these things. We'll get back to that problem later, but I can tell you right away that this set is going to be infinite. This class x, k. And the reason it's infinite is that there's, what is it? I think it's 525, but that may have changed. So that's Erdös theorem, one of the many, 1959. And it says that for all k, there are graphs whose chromatic number is at least k, but also whose girth is at least k. Right? So you can have large chromatic number as large as you like and large girth as large as you like, both present in the same graphs. Why does that imply that this is infinite? You see that? Yeah? Well, you can make yourself elements of this using that theorem. Suppose you found one, right? One element, or none, it doesn't matter, in here. You can create a new one that is bigger than that. How do you do that? Well, suppose those that you have found already all have at most 135 vertices. Then you put k equal to 136, and then this theorem gives you a graph that has chromatic number bigger than k and girth bigger than 136, or at least that, right? So that contains a minimal graph of chromatic number at least bigger than k, and this subgraph still has the same girth at least. It might have even bigger girth, but you won't in a subgraph suddenly find short cycles. So that'll be a graph of chromatic number bigger than k of girth large enough that it can't be an element of these by choice of that girth, which is bigger than the oldest of those graphs already found in there. So that's an additional element. So for every finite set of elements that you have already found, you can find another one. Okay, so what does that mean? Incidentally, this is a famous theorem for all sorts of reasons. One is it's really, really fundamental. It crops up everywhere. Another reason is that it puzzled people for a long time because it's quite difficult to construct such graphs. Right? So the original proof is probabilistic, which does not mean that there probably is such a graph, or maybe not, but with high probability or something. It means that there definitely is such a graph because in some suitable probability space, the probability that such a graph exists is bigger than 0. And if you set this up formally, as you learned in probability, then the probability of something being bigger than 0 means that there exists such a something in that space. So this probability statement that we make up for the proof, or that Erdös invented for the proof, will imply the definitive existence, nothing about probability, that is asserted here. And that's become known as the probabilistic method in combinatorics. It's a huge thing now, and that was the first, or one of the first theorems in it. Okay, so why are they hard to construct? Well, if the girth is large, then locally, you've seen this picture before, so locally around every vertex, the graph looks like a tree, right? You can't, when you look at the neighbors and then the neighbors of neighbors and so on, you keep generating new vertices because if they were the same, you'd have a short cycle. Now, in a highly chromatic graph, there's a subgraph of large min degree. So let's look at that subgraph and let's look at its structure from the point of view of any particular vertex. So this is large min degree. All these vertices branch out. And they do that in a tree-like way for a long, long time. And then at the end of the day, the leaves of that tree you got to, I mean, this graph is finite, so you can't do that forever. But these have to have large degree as well. So these edges have to go somewhere. But they can't go to close vertices in the tree that you have generated, because then if these two went to other vertices like those two, you'd have a short cycle. So these have to be somehow spread in a clever way, and it's not so easy to come up with a clever way that does that explicitly. So to construct a graph of high girth and simultaneously high min degree, never mind the chromatic number, is quite a non-trivial thing to do. Such constructions do exist now, but the probabilistic proof is much, much prettier and also much simpler. Right. So let's get back to trying to come up with such a set xk, even if it has to be infinite. So we want a Kuratowski set, something like it, for high chromaticity. And I mean, even if we know that this class is infinite, there might be a very simple rule telling us how to construct them. So it might be interesting or useful all the same. And the theorem I want to show you gives a very simple construction of all these graphs, or more precisely of a superset or superclass of that graph. And that is Hajós' theorem. And let me just give you Hajós' construction. Call the following graphs k-constructible. Call the following graphs k-constructible. First, kk. Okay? So the idea is to construct a superclass of x, k. So they should definitely all have, okay, at least k, need at least k colors. So this certainly needs k colors, so that's fine. Second rule, if we find two non-adjacent vertices, in a graph that is already known to be k-constructible, then identify these to get another k-constructible graph. So graphs obtained from k-constructible graphs by identifying two non-adjacent vertices are, by this rule, defined to be k-constructible as well. Right, so that's a recursive definition. We're assuming that we have defined some earlier things before, and we're using that like the k-constructibility of this hypothetical graph G. Right, this is a little tedious to write down, so we don't have a formal notation for identifying non-adjacent vertices. So the way I wrote it in the book, don't be sort of alarmed, is by adding this edge and then contracting it afterwards. Right? But that's only for the notational reasons. So what's really happening is that we're identifying two non-adjacent vertices. And the third is similar. So if we have a graph G1 with a vertex x and a vertex y1 that is adjacent to x, and we have another graph with a vertex also called x and a neighbor of that called y2, then identifying these two vertices and adding this edge is also k-constructible. right? So you have one k-constructible graph, and deleting those edges. So you have two k-constructible graphs given, G1 and G2. Each has an edge. Then you take a vertex of this edge in each of the two graphs, and you identify those two. Just those two vertices. All the other vertices remain disjoint or distinct, right? And then you add this edge between the two neighbors, y1 and y2, and you delete the original yix edges. Okay. So let's just check. These graphs, do they need at least k colors? Well, if G already needs k colors, then identifying two non-adjacent vertices will not reduce the chromatic number, because if you could color the green graph with fewer colors, you could expand that pair again, and you could keep that coloring with fewer colors because they're non-adjacent in G, right? So the identified graph will also need few colors. Notice that we're making the graph smaller here. Here we're making it bigger. So let's check here if G1 needs k colors and G2 needs k colors, then why does this graph constructed from the two also need k colors? Well, for a very similar reason. If it could be colored with fewer colors, then that would induce coloring with fewer colors in either G1 or G2, depending on how these two vertices are colored. So that's all easy. And the theorem now is, so that's 1961. If a graph needs at least k colors, so that's for k. If a graph needs at least k colors, then it has a subgraph that is k constructible. Right, one of these specific graphs that need at least k colors. Right? So I'm not saying that we've found this set. That has the same property, that every graph that needs at least k colors contains a subgraph in here. And we're now proving that every graph that needs at least k colors has a subgraph that can be constructed in this way. But it's not the same class. Actually, it has been shown since that these graphs are all of them. But let that not bother us for the moment. Let me just prove this statement. So, proof of Hajós. Given a graph with chromatic number at least k, we find k constructible h in k. Now, we can assume that G is edge maximal without a k constructible subgraph H. All right. And then let's get a contradiction. Okay, so then what can we deduce from that? First thing to notice is that G is not complete multipartite. Right? It's not like this, with all edges between the classes, but no edges in the classes. Because if it had this structure, how many classes would there be? Well, if it needs k colors, then there must be at least k classes. If there are fewer classes, we could take them as color classes. Right? So if it's complete multipartite, then there are at least k classes, but then pick one vertex from each of them to get a kk subgraph, and then we have found a k constructible subgraph in G after all, or we have a contradiction, whichever way you prefer it. Okay, so it's not that. Hence, and this is a silly little way of rewriting that statement, but it's one that crops up a couple of times in graph theory, so let me just write it. Non-adjacency, this is very, very sort of overblown. Non-adjacency is not an equivalence relation. Right? I mean, that sounds a bit like post-constructionism or something. It's really French. Non-adjacency is not an equivalence relation. What does that mean? Well, it can't be, because if it was, we'd have the equivalence classes, these maximal sets that are non-adjacent, and that will be precisely the structure. So that's the same thing. Okay, therefore, there exists, shall I put this here? Yeah, why not? There exists a violation of transitivity of non-adjacency. How can non-adjacency fail to be an equivalence relation? Well, it can't fail to be symmetric. It can't fail to be reflexive, but it can fail to be transitive. So if it fails, it must fail to be transitive. So there are two vertices, three vertices. This is equivalent to that. That is equivalent to this. So these are non-adjacent, those are non-adjacent, but this is not equivalent to that. Okay. So that exists somewhere in G. Okay. Let's give these things names. And as you might have guessed, y1, y2, and x. Now, if we add this edge, then because G was edge maximal without a k-constructible subgraph, there will be a k-constructible subgraph. And similarly for that edge. All right. Now, if it so happened that these subgraphs meet only in X, That would be lovely. Because then we'd say, okay, we have the blue subgraph with this edge here, and we have the green subgraph with this edge here. Now we make those two neighbors adjacent and delete those edges. And voila, what we have is a subgraph of G. That'd be lovely. And we're not far from that. Why? Because there may be other vertices in the intersection. But we now do a trick. We create a copy. So let's call this H1 and call this H2. And let H2 prime be obtained from H2 by replacing every vertex in the intersection of H1 and H2 with a clone. Right? So these vertices are all sitting there in the blackboard, and the orange vertices that are in the intersection of both, you make a copy, put it slightly, raise the copy above here, and make these vertices in H2 adjacent to each other and to the other vertices of H2 as they used to be when they were still there. But they're different vertices now. Right? Now we have H2 prime and H1 that really do intersect only and exactly in X. And it's quite okay if Y1 or Y2 or both are orange. I don't care. Because now, the union of H1 and H2 prime, followed by the addition of this edge and the deletion of those two edges, is going to be K-constructible by that rule. Now we've found a K-constructible graph that, however, is not really a subgraph of G. But how does it differ from a subgraph of G? Well, it differs in that these clone vertices exist twice. Each of them exists twice. But a vertex, an orange vertex, and its clone are never adjacent, because we didn't make them adjacent. So we can apply 2 and identify them again. And there we are. That's the end of the construction. Right, and notice that this edge here is really missing from the union of H1 and H2 prime. Even if Y1 is orange or Y2 is orange or both are orange. Right, this edge is from an H1 vertex, which is definitely not in H2. Why not? Either it wasn't in H2 to start with, it's not in H2 prime. Either it's not even in H2, or if it was, it got copied, and only the copy is in H2 prime. So Y1 is certainly not in H2 prime, and Y2 prime is definitely not in H2. Either it wasn't to start with, or if it was, then it isn't now after it got primed, because it's a copy. Right? So this is the edge from from Y1 to possibly Y2 prime, if Y2 was in the intersection, otherwise just Y2. Yeah, questions? Good. So, post-mortem. I said, even if this is infinite, it might still be an interesting class. Is this an interesting class? Let me make that question easier. Assume you're a computer. Are you finding that class interesting? No, you're not, because you haven't a clue what it is. I didn't give you a list of these things. I gave you a construction, but the construction, you can't use the construction to produce a list. Why not? Because it goes up and down. You can't say, if I let the construction run for 1,000,000 steps, then I know for sure that I've found the first 102 k-constructible graphs. You don't know, because they get bigger and they get smaller. You never know whether you've got the first 100, no matter how long you run, you the computer. Right? So we don't even know how to construct, how to make this list explicit, and we certainly don't have certificates for needing at least k colors, let alone easily checkable certificates. We don't have a definitive list of certificates. And if I give you the computer a graph and ask you, is it k-constructible? Do you know? No, you don't know. You might find a k-construction, or you might not. And if you don't, then you can't say, no, it isn't. You can't say, haven't yet found one. Right? So you can't decide whether a graph is in this class, let alone quickly. Right. Even if I give you that graph, not to mention I give you a graph and ask you, does that need many colors? And you say, oh, well, just wait a minute, I'll just check whether it has any of those as a subgraph. That's an even taller order, and that's even further away. And so the existence of easily, quickly checkable certificates for high chromatic number is, in fact, one of the biggest problems in mathematics. Certainly in combinatorics, so that's the problem whether the decision problem of whether an input graph can be k-colored with at most k colors is in co-NP for the computer scientist. And you're a human again, so, but you might be a computer scientist now, and that's how you would rephrase that. And yeah, so much for that. Interesting side remark, history has shown so far that this Hajós theorem isn't even interesting or hasn't become important in any theoretical way either. I don't know of any theorem that uses it, which is maybe not so much a surprise, but one can't always tell. Sometimes things that are difficult for a computer can be edifying or enlightening for humans, but in this case not. So imagining to be a computer is sometimes a good idea. Right. Okay, next section, edge coloring. An example of an edge coloring problem, here's one. If you take just a bipartite graph and it has the left class of vertices as the set of teachers at some school, and on the right you have the classes that need to be taught, and then you, for every teacher, you put an edge link, you join the teacher by an edge to every class that he or she has to teach, and every class gets joined to the teachers that need to teach that class. And the scheduling problem, yeah, let me call it, the problem of making a timetable is an edge coloring problem, right? So if you think of how many slots you need, so that in these slots, all the teachers can teach all the classes that need to be taught. A slot is an edge coloring, is a color class, or has to be a set of non-adjacent edges, right? When this teacher teaches that class, he or she can't at the same time teach that class. So two green edges, adjacent edges, because they're using the same teacher, have to be scheduled at different times, and the same goes for classes. So the minimum number of time slots that you need corresponds to an optimal edge coloring of this graph. And there's a fun little way of translating the Latin square problem into the problem of edge coloring KNN. So just think about it for a moment. I don't want to go into that, but it's immediate. So, the edge coloring number, or the chromatic index, is obviously at least delta, the max degree, right? If you have a vertex of any vertex, you need at least as many colors as this vertex has incident edges, because adjacent edges need to be independent, colored differently. And the first theorem I want to show you is another König theorem. That's 531. Right? It says 1916, golly. And that is when G is bipartite, then we have equality. Right. Okay. So let me prove that. Proof induction on the number of edges. consider an edge xy and delete it. By induction, there is a delta coloring, edge coloring of G minus this edge, where this delta is the delta of all of G. Right, there is even an edge coloring by induction of the reduced graphs, big delta, which might be smaller, but there's certainly one for our delta. Now, look at this coloring. X has fewer than big delta neighbors in G minus X, Y. So we're not using, this coloring doesn't use all the available colors if we want to color with delta colors. So let's say that color alpha is missing in this coloring at the vertex X. And say the color beta is missing at the vertex Y. Now, let's construct a beta alpha path out of X, a bit like as in the proof of Brooks's theorem, except now we're coloring edges. So we start, alpha is missing, there's no alpha edge at X, but there might be a beta edge. If not, then the path we're constructing is trivial, it's just X. So maybe there's a blue edge out of X, then we get to some vertex. At this vertex there's at most one green edge. It gets us to another vertex. There's at most one blue edge out of that, and so on. And this has to stop at some point, right? Because we're in a finite graph. I'm giving you a slightly incomplete proof. Warning. I'll complete it later, so I'm not going to make real errors. Yeah. So let's consider a maximal such beta alpha path out of X. That is finite because the graph is finite. And then we can say, okay, then along this path, just swap the colors, blue and green, alpha and beta. And after swapping, it's not alpha that's missing at X, it's beta that's missing at X. And then we can color this edge with beta, and we're done. Okay, end of incomplete proof. Where is the gap? Anybody notice? Well, of course, I noticed where I wanted to introduce the gap, and after I did, I told you this is going to be an incomplete proof, so you may remember what I said at the time, or had just said. The one gap is to say that, well, I said this path has to end because the graph is finite. But that's not an argument I want to use, because if we have this path like here, then maybe there's always at most one edge to continue, that's right, but we want to deduce from the fact that the path ends here that there is no edge out of it with the color required next. And there's no edge out of it with the color by which we arrived, because there's at most one. So we can recolor, and after recoloring it, this vertex is still okay. All the other vertices remain okay because they're adjacent to both colors and will be adjacent to both colors after the swap. X will just change from a missing color to another missing color. But at the last vertex, we need to show that after recoloring the edge by which we arrived there, we're not making that, giving that a color for which an out edge already exists, so that we have a conflict there. And the way we want to argue is that, well, if this edge existed, then we could have continued. But I said this has to stop because the graph is finite. So there might be a different reason why we can't continue, and that is that we've arrived here, and continuing would get us to a vertex we had before, so the extended thing wouldn't be a path anymore. That might be the reason for the maximality. And if this happens, then, of course, swapping colors here will land us with two blue edges of that vertex. So that argument was slightly incorrect. Of course, this cannot happen because there's a green edge into this and a blue edge out of that already on this bit of path here, and we can't have another edge of one of these two colors going into it. And similarly, if this hitting vertex was the starting vertex, then one color goes out of it, blue, and the other is missing, so we can't have that either. Okay, so that would fill the first gap. The way I wrote it in the book was to say we don't choose a maximal path, we choose a maximal walk. In that case, this would be allowed technically, and we just have to prove that it doesn't happen. So we prove that this walk is in fact finite and is a path. And then we can do the argument. And there's another gap. Yeah? That's right. Yeah. So it might happen that, so out of y, we could have an alpha beta path, and it just conceivably might happen that we end at y. Can it happen? And in this case, nothing will be gained, so this recoloring process would change the missing color alpha to a missing color beta here, but here the missing color beta would change to a missing color alpha. So, and the other color would always be present, so we couldn't color that edge with either color even after swapping. But it can't happen. Why can it not happen? Yeah? Yeah, that's an odd cycle. Okay, good. Other questions? Right. Okay. Oh, we're doing quite well. Then let me prove the big theorem for the day. And that's Vizing's theorem. That's 1964. Not so much after Hajós. And that says that one more will be enough. Okay, in bipartite graph, we even achieve equality right here. This is trivial. In bipartite graphs, this holds with equality. We've just proved that. And in arbitrary graphs, we only need one more. So that's a big thing. So let me prove Vizing's theorem. So we'll do induction on the number of edges again. let G be given. And we write down something to remember before we continue, and that is the following. We may assume for every edge xy of G, and for every delta, delta plus 1 coloring of G minus xy. And as before in König's proof, this delta is our delta. It's delta of G. For every delta plus 1 coloring of G minus xy, if alpha color alpha is missing at x and beta at y, then the alpha beta path out of y in G minus xy in the graph that we've colored out of y ends in x. All right, so that's something we may assume. Why is that so? Well, if we have our x and we have a y, and we delete this edge, and then we have an alpha beta path out of y, alpha, beta, alpha, and so on, then if it didn't end in x, we could do precisely what we did in König's proof. We could recolor this entire path. We'd take a maximal such path or a maximal walk and then prove it's a path. And if we didn't get home to x, we could just swap the colors along that path, and that would result in this edge being changed to beta, and alpha would afterwards be missing here, and alpha is also by assumption missing at x. We could color this edge alpha. Okay, so we may assume assertion star for any edge xy. Okay, so now pick x any vertex in G, and let's say pick an edge xy naught in G, and let C naught be a delta plus 1 edge coloring of G minus x, y naught. Okay, so in G, we pick any edge. One vertex is going to be called x. Let alpha be missing at x in C naught. So we're coloring this graph G minus this edge by induction. And in this coloring, some color must be missing at x. Even two colors must be missing at x, because x has degree at most delta minus 1 now, and we have delta plus 1 colors. So there's certainly a color missing at x, and let's call that alpha. So alpha is missing here. I want to indicate that by a little minus. That is a minus, this dash here. Okay, now I'm not going to write the entire proof here, but I'll continue with the drawing. I hope an intelligible drawing. So at the vertex y naught, there's also a color missing in C naught. Say yellow. Now let's look. Is there an edge out of X that is colored yellow? Yeah. Or else we'd be done. If there wasn't such an edge colored yellow out of X, we could just color this edge xy with yellow. So the color yellow does exist at X. It's not missing at X. Okay, so let's call this y1. At y1, there's a color missing. Oh, you can't see that. So blue is missing. Is there an edge out of X colored blue? Yes, there is. Suppose there isn't. Suppose there's no edge at X colored blue, then we could color this yellow edge with blue rather than yellow and use the yellow edge for here. All right? You get that? So once more, we're always talking about our coloring C naught. Question?
Blue and alpha is not the same here, right?
Oh! Thank you, thank you. Okay. Right, so if there wasn't an edge at X with the color that's missing at Y1 in C naught, we could just color this yellow edge with a missing color instead and use the yellow to color this, and so on. So here there's another color missing. This white here is green. And then there must be a green edge out of there. For the same reason, if there wasn't a green edge at X, we could just color this green instead of red, use red for this instead of yellow, and use yellow here. And so on. Now, continue in this way as long as possible. Important, with distinct new vertices. Always ask, is the missing color at the last vertex or pick a missing color at the last vertex, and ask, is there an edge with that color at X? But I don't want to consider earlier edges. So it might be that yellow is missing here, and I don't want to say, oh yeah, here. Not just yet. So I'm just asking, is there a new neighbor of X such that the edge from X to that neighbor is colored with the missing color here? And we do that as long as we can until we get to a vertex, call it YK. And here the argument is, again, this must stop because we're in a finite graph. We can't come up with new neighbors of X more than delta times. So let's look at what happens at YK. Let beta be missing at YK. So yeah, that's visible. Okay, that's brown. Now consider, let P be the alpha beta path out of YK, but not in C0, but in the coloring of G minus XYK, G minus this edge, but with that edge still, with respect to the coloring CK. C0 plus push. That's my definition for CK. So let me show you what, yeah. You start with C0. We want to color the graph G minus this edge, but with including that edge. How do we do it? Well, we don't have to color this edge because it's no longer there. But the color of this edge in C0 is missing here. So we take this to color that edge. Then this filters down all the way, as I showed you earlier, to produce a coloring of the entire graph, including this edge. Entire graph minus this. Right, so that's the coloring, what I call CK, and similarly we have it for every YI on the way, right? YI is the coloring of G minus the edge XYI. CI is the coloring of G minus XYI, where the coloring that this edge gets in C0 is not used for it because this has been deleted, but it is used one further down. and then the color that is freed one further down is used one further down, all the way up to down here. So that's the definition of all these coloring Ci of the graphs G minus xyi, all the way up to I equals k. Okay, so now we take this alpha beta path out of yk, and it starts not with beta because beta is missing there. Oh, sorry, beta is missing there in C naught. Is it also missing in CK? Yes, certainly. CK here has exactly the same edges and with the same colors as in C naught, except this one got deleted. Right, so in this graph here, beta is still missing at yk and the coloring ck, so we might be able to start with alpha, or might not, and we do that as long as we can. And how long can this go on for? Well, we have a coloring of G minus some edge xy. This y is yk now, where alpha is missing at x and beta is missing at y. Now we remember this. Right? Whenever we have an edge xy, and we have a coloring, in this case it's ck, where alpha is missing at x, yes it is, and beta is missing at y, yes it is, then this alpha beta path in G minus xy out of y ends in x. Okay. So how does it end in x? Well, not with a blue edge, because alpha is missing. So it must end there with a brown edge. So actually, let me redraw that picture. By giving this another color. Okay. So this path, this yellow-blue path, goes all the way back to x, and it gets to x with a yellow edge because there are no blue edges at x in C naught, but also not in CK, because the colors used at x don't change in this pushing down thing. In the pushing down, we always used a color further down, further down, further down. So we never changed whatever colors are used at x. So we get to x by a yellow edge. Now, is this one of the edges already used, as I drew it here? Yes, it is, because if it wasn't, if this was a new edge, sort of something up here, then this was missing, and I asked this vertex yk, is your missing color used for a new edge? And it said no. By maximality of k. Okay, so nonetheless, this path exists and it has to end at x, and all we know is, but we know now that it ends with a color beta, with an edge colored beta at x. Okay. Now, careful. So the picture is now misleading because this yellow color is a color not in C naught. It's a color in CK. Right? I chose this path in C with respect to CK. But still the argument holds. It's a path with respect to some coloring, CK, that starts at some y with a color missing there, and it must end at x with an edge that is not missing it, x. So this edge can only be beta. So this is colored beta in CK. Why is it colored beta in CK? Because the next edge up, and it exists. I mean, it might be this, but it exists. The next edge up is colored beta in C naught. That's how this got its color in this pushing down thing in CK. So this beta is used in C naught for the next edge up. But that means it was missing at this yi in C naught. So beta is missing at this yi in C naught. But now I consider the alpha beta path let yix be its last edge. And we got that by applying star. That is really incident. That it's an edge of that form. That's the last edge of this path here. This is, okay, then CK of this edge, yix, is beta, as alpha is missing at x, hence C naught of yi plus 1 x is beta. That's how it got its color in CK. So beta is missing at yi in C naught. Now take the alpha beta path out of yi with respect to ci. So in ci, since this is missing in C0, this beta, it's the same argument. In ci, in ci, yeah. Then, okay, this is P backwards. Which is a contradiction to star. So why is that C backwards? We take the alpha beta path out of yi. Start with alpha, then beta, then alpha, then beta, and so on. All these edges here have the same colors in all the colorings we've so far considered, C0, CK, and CI, because we only ever changed colors of edges incident with X. So we can take the alpha beta path out of yi with respect to CI. And now we have an instance of this. We have an edge xyi. And when we delete it, we have a coloring, namely CI, whose alpha beta path, where alpha is missing at x, yes, and beta is missing at y. It's missing at y in C0, and therefore also in CI. Has to end at x, but it doesn't. It ends here, because this is an alpha edge, this last edge, and there's no yellow edge, there's no beta edge out of yk, because beta is missing at yk. And that's the proof.